what we have done so far is we've done bipolar junction transistors. Now, the BJT transistor that we've done so far that I've taught you is working with a current. And we know that the current that flows in a base will be multiplied by the gain, and then that current flows in a collector. So with field effect transistors, there is a different way of working, and a field effect transistor does not work with current. It actually works with voltage. So it's really a voltage amplifier. So the difference between a FET and a BJT transistor is basically, firstly, it is a voltage amplifier, if we ask you that in the exam. And then the other thing, it is unipolar. Unipolar means it is only has like an N material or a P material. So, and it forms a channel. I'll go to a picture just now to show you, but BJTs are bipolar. That's also a difference between them, and FETs are unipolar. Right. So BJTs are current controlled and FETs are voltage controlled. And it also has 3 terminals. The FET has got 3 terminals, just like a BJT. For the BJT, it is base emitter collector, but for a FET, the field effect transistor is a FET. For a FET, we've got a gate, a drain, and a source. Now, the gate is very similar to the base. The source is very similar to the emitter, and the drain is very similar to the collector. Also, in a FET's case, the drain is a bigger junction point, and the reason for that is it handles more voltage and current, so the wattage is more, the heat is more on the drain pin. So the drain pin is the biggest pin. So I will start now going into a little bit theory and then really actually how it works. You guys can ask me anytime, you can ask a question. So we've said it's a 3-terminal voltage controlled unipolar device, and they depend on the type of charge character. The carrier either free electrons or holes, which is similar to normal transistors. Now there are 2 types of FETs. The junction field effect transistor, which is a JFET, or the MOSFET, which is a metal oxide semiconductor field effect transistor. It's a long word, but we have to know the difference between these 2. So FETs are voltage control devices, and the input voltage controls the output current really. So we can pull 2 volt or 3 volt in, and we can get 2 amp or 3 amp out of it. That is basically to convert a voltage to a current. While BJT is really a current input and a current output. Right. They have very high input impedance, in other words, on the gate of the MOSFET, which represents the base of a BJT transistor. It's a very high input impedance, so very high input in resistance basically, and they require very little power from the driving source. In other words, there's no current flowing in the gate, almost no current. Right, so this is the construction of the FET, and in this construction we can see that the drain is on top, and then this one has got a gate 1 and a gate 2. Usually we only have 1 gate, but in these very old type JFETs, they've got 2 gates. And then at the bottom, we can see there is the source. So the gate is where you apply the voltage input, and the drain, the positive to the battery, and the source here at the bottom goes to the ground. Now, on the left, there's an N channel, and there's an N here, and we call it the N channel. It's a channel here between the gate 1P and the gate 2P. So that channel goes from the drain to the source. Now, On the right-hand side, there's a P-channel FET. And I'll show you now the electronic symbols for a FET2. And this P-channel FET has got a positive channel, while the N-channel has got a negative channel. Right. And let's talk a little bit about the characteristics. A FET is basically 4 legs. Only a JFET. The MOSFETs that we use in modern days these days, they only have 3 legs, just like a normal transistor. But this FET, the JFET, has got a drain, source, and the 2 gates. The area between the source and the drain, like we told, there's a channel, and this channel is either N channel or a P channel. Now, embedded on each side of the N channel is 2 smaller P regions, which is the gates, and they are positive regions. Let me just go back to the picture again, and you see here with the N channel gate, the gates are positive on each side. So, and on the P channel gate, the gates are negative on each side. So the P channel gate is positive in a channel, and the gates are negative. So remember that. Right. Now, when separate leads are connected to each gate, the device is called a dual gate, JFET. But usually we only use one gate, and only one gate is really necessary, and we sometimes leave the other gate not working. The current flows between the drain and the source terminals. Just like a BJT, the big current flow is between the emitter and the collector. But here in this case, it's the drain and the source. The drain on the top at ground, and the source is on the positive side of the battery positive side. Sorry, the drain is the positive side. The source is the negative on the ground. For the N-channel JFET, the majority current carriers in a channel are free electrons. For a P-channel JFET, the majority current is holes. Now, for FETs, unlike bipolar transistors, for FETs, the current is always majority carriers for both the N-channel and the P-chip. So remember this, majority carriers. So if I ask you in an exam, is bipolar transistor and a FET, which one is majority and which one's minority? So for FETs, they are always majority current carriers. Right, any questions so far? Right, now the schematic symbol for the FET. On the left here, picture A is the drain on top, where your battery is connected, the plus voltage, and the source is on the bottom, which is your ground. And then the gate is on the left, that's your input there. And we give a voltage to the gate, not a current like a BJT. In the middle one, the left one is the N channel, and anyway, when an arrow goes into it, it's N channel. B is a P channel where the arrow goes out of the gate. You see that arrow. And then on number C is an N channel asymmetrical FET, which is got a gate on the one side, and that's as close to the source. Normally, the sign for it is a left 2, which we use for all cases actually. In normal cases, we use these 2 on the left for the JFET picture, the symbol. This is the symbol that you'll find on your circuit diagram. That's the symbol we use on the circuit diagram. Right, so okay, I've done this basically. And then how do we apply it? So we put the battery there on the drain on top, and the drain current or basis basically flow the electron current. The electrons is ID in a clockwise direction, but the conventional current, which we always use at TUT, goes up from a battery, left here, and then down into the N-channel FET. And then the 2 gates are positive with the channel is N, So it forms like a groove. In real life, they actually make a little groove here. That's why they call it a channel. And that groove has got very low resistance. And the current will then move from the drain towards the source. Right, the operation. With the gates disconnected, the amount of current depends on two factors: the value of the drain source voltage and the drain source on the resistors, RDC, RDS. So there is a resistance between drain and source over that channel. It's got a resistance there, and we must remember that. But the ohmic value of the R drain source depends on a few things. It depends on the doping level. So when we manufacture it, we determine that. Okay. So the more expensive ones are doped more, and they will have a very small RDS. RDS will be typically these days about 10 milliohm. That gives you an idea, RDS of 10 milliohm typically these days. Now, it also depends on a cross-sectional area, in other words, how big the FET is, and also on the length of the channel. So the resistance is determined by the doping level, the cross-sectional area of the channel, and also the length of the channel. Right, now in this figure here on the left, electrons flow from a channel from the source to the drain, but the conventional current flows the opposite, anti-clockwise. Now in a JFET, the source current and the drain current are the same. So not like normal transistors where the emitter current is base current plus collector current. No, not in this case. In this case, the source current is always equal to the drain current. And the reason is in this gate, there's no current flowing in the gate. That's why. Okay. So the action of the gate. So if we take the gate and we fasten it to the source, so we ground the gate here. In this case, picture A. In that case, we apply no voltage onto the gate, and there's 0 volt on the gate, which is the same as the source. Or we can take the gate and we can put a negative battery there, a negative voltage, not a positive voltage like with BJTs. In this case, the battery must be a negative voltage applied to the gate. And that gate and the other gate are together. Say it's connected to -4 volt. You see. But however, the drain, we still connect to the battery plus voltage, like the BJT transistors. So in this case, on the right-hand side, the current will start flowing through the transistor. And in the left-hand case, it will be off and no current will flow. So in figure A, there's 0 gate current, and it's reverse bias. That's why the drain source current doesn't flow. So guys can read these notes here. I'll put these notes also on Brightspace for you. Due to different doping levels, the depletion layers penetrate deeply into the N channel and only slightly into the P-type, like they show here. The doping is only slightly into the channel. So the B figure, which had -4 volt on the gate, remember I showed that, is now normally biased. It's got a bias voltage, and the bias voltage in this case is -4 volt, like we said. So the drain made positive relative to the source, and the gate made negative relative to the source. A bit strange. BJTs does not work exactly like this. It's like the gate is like opposite, with a negative voltage on the gate. The negative gate voltage expands the width of the depletion regions, and then that channel will narrow, just like a BJT where the the two bands, the conduction band and the valence band, will become narrower as long as there is a voltage on it. In this case, it's same, and the channel will narrow the moment we put a negative voltage on the gate. And a narrow channel means reduced drain current. By varying the gate source voltage, the drain current can be controlled. So we're varying the voltage on the gate source, and therefore we're controlling the current on the output. So when gate source is made negative, it pinches off the channel, and the result is zero drain current with a very negative voltage, say minus 10 volt. So there will be zero drain current flowing. The amount of VGS required to reduce the drain current to zero is called the gate source cutoff voltage. So there's a gate source cutoff voltage. And in the data sheet of this IC, when you buy this transistor or this FET, it will tell you that voltage, the gate source cutoff voltage. The polarity of the biasing voltage for the P-channel JFET is opposite than from an N-channel. So remember, for the N-channel, the positive is on the top, which is the drain. But for the P-channel, the negative voltage is on the drain and the positive voltage is on the source. So this is basically just the same for bipolar transistors as well. So we've got now a circuit here, and we've got a voltage there on the drain. This is the N channel because the arrow shows into the gate here. So this is an N channel gate with a positive voltage there on the drain. The source is connected to ground, and we've got minus 4 volt on the gate. So that minus 4 volt of the battery here on the left. Minus 4 volt on the gate. So what we now have, when there's minus 4 volt on the gate, basically the drain source current is, here's an example actually, minus 4 volt on the gate. The drain source current really is very low, maybe 1 milliampere. However, when I put minus 2 or minus 3 on the gate, minus 1 on the gate, like in this graph, and you can see then the drain current is only about 5 milliamp. Get a full 10 milliamp out, we must put the gate at 0 volt. Then the full current is going through the gate. This is just the opposite of a BJT, where the highest voltage will give you the highest current at the output. In this case, the most negative voltage will close the channel totally so that no current flows on the output. So this picture here, you can remember this picture roughly, that the more negative the gate is, the less current goes through the drain source junction. People, are there any questions about this page? This really tells you what current voltage you put in to get the current output in the drain there. Are there any questions on this? When this gate, when there's no battery here, and we short the gate to the ground here, then this graph works, and basically the 10 milliamp current flows in this region through the drain source. 10 milliampere current will flow with no battery voltage, 0 volt there. Right. So the shorted gate source junction, we already explained that, is when there's 0 volt in it, then it's in a cut-off position, and therefore there's no current flowing in the drain source. The maximum drain current that the JFET can have occurs when the gate source is 0 volt. the maximum current will flow. All right. Now this is called drain source current with the gate shorted. However, as the drain source is increased from 0, so the voltage are increased, the drain current increases also. So the power supply over the FET, if we increase that voltage, the current will also increase proportionally. So when the voltage on the gate reaches the pinch of voltage, the drain current becomes 0. So this is that -4 volt that we put on. If we put -4 volt, which is the maximum voltage, we call it the pinch of voltage. The pinch of voltage means we switch the FET basically off and there's no drain current flowing. That's what that means. Are there any questions on this, people? Let's carry on and finish as quick as we can without holding you up. So above VP, the VP is the current source region, so where ID is unaffected by changes in the V drain source. What that basically means, above the VP voltage, right? It means that ID is unaffected because it's already a 0 current. So even if we increase the drain voltage here, the current will not increase. It will be very close to 0. All right. The drain current levels off above the pinch off because the N-channel resistance, RDS, the resistance of the drain source channel. Remember we said the drain source channel has got a resistance. That resistance will increase in direct proportion to V drain source. So if I double V drain source, the voltage over it, then that resistance will also double. So the resistance will double when I double the voltage over the FET. FETs get very strange properties and we just have to get notice or take notice of them, and you have to learn this theory. JFETs are often referred to as normally on devices. In other words, even if we don't give a gate voltage and we make the gate voltage 0 volt, it means the current will still flow. So they are normally on. Normally on means the current will flow from the drain to the source. The drain source current will flow with 0 volt on the gate. Right. As soon as I made -4 volt on the gate, it's the pinch voltage we talked about here, the pinch voltage, and then the drain source current becomes 0. So these are the two extreme cases. VP is -4 volt, no current flowing, or the gate is 0 volt, which means the current will flow and it's normally on. All right, we already looked at the graph for the drain curve. This means this is the current through the drain source current. So that current is 10 milliamp. In this case, when we've got 0 volt on the gate, I said it's on and the current flows. However, as I go -1 volt, -2 volt, -3 volt on the gate, then the current here will be 5 milliamp, 4 milliamp, 3 milliamp, and 0 milliamp. So it will stop flowing at this point where I've got like maybe -8 volt here. There will be no current flowing. So the pinch off point is roughly about here at the bottom. Maybe in this case, maybe about -5 volt is the VP, the pinch off voltage. Right. No, not the following. But VP, the pinch off voltage, is equal to a minus voltage. So it's a negative voltage, and it's the voltage over the gate source. In other words, a negative voltage over the gate. Like for instance, in this case, it was -4 volt all the time. Now the pinch of voltage in this case is -4 or -5 volt, and it will stop the drain current in this case. Right, the slope of a drain curve in the ohmic region decreases as V gate source become more negative. So the voltage becomes more negative because our drain source will increase, that resistance will increase. That allows the FET to be used as a voltage variable resistance. So a FET, one of the applications for it, if we ask you what are the applications for the FET, a FET application can be to make a variable resistor. And because it increase or decrease the resistance between drain and source. That is why. So we can make a potentiometer or a variable resistor, which is now, for the first time, electronically controlled. So we control it with a voltage, and if the voltage is -5 volt, a very high voltage, that resistance is very high, and when we make the gate source voltage 0 volt, that resistance is very low. Right. The drain source voltage where the pinch off occurs, in other words, where VP is like more -4, -5 volt in that region. So that the VDS will then decrease as VGS becomes more negative. I've said this point over and over. So at pinch off, the voltage on the gate source becomes more negative. For instance, it becomes like -4 volt, -5 volt. That's an example of this 0.3. So the voltage over the drain source equals to the pinch off voltage minus the gate source voltage. So what this means, the pinch off voltage is actually a voltage. Let's make it -5 from now on, which the data sheet tells you it will pinch off at that point. It will be -5. So if the gate source voltage is like -2 volt, then the drain source voltage will be this -5 -2 volt. In that case, -5 -2, so will be about this voltage will be about 3 volt between the drain and the source. So we can control the voltage with the pinch off voltage and the gate voltage, the gate source voltage. That's what we use to control the voltage over the FET. So where VP, like we said, is the pinch off voltage, at VGS is 0 volt. And VDS, the drain source voltage, is the pinch off voltage for any value of V gate source. Don't worry so much about this last point. It's not really important. As long as you understand about the pinch off and the formula, this formula, just also remember to learn this formula. So we've got a pinch off voltage and we've got a gate source voltage, and therefore we can now calculate the drain source voltage at pinch. That's why there's a P in brackets here. So what we also have for a FET is a transconductive curve, where we've got now minus voltage on the gate here at the bottom, a minus voltage on the gate, and therefore the current in the drain source will start flowing 2 milliamp, 5 milliamp. More current with a lesser voltage, very close to 0 volt. However, -4 volt, the current will be very low, about less than 1 milliamp of flow. So it just shows you the drain current versus the voltage on the gate. The graph is not linear, so this is not a straight line here. This is not a linear straight line where y is mx plus c. No, this is more sort of an E curve, this line. And it's because there are equal changes in VGS and do not produce equal changes in ID. So the drain current and the gate voltage are not linear with respect to the other. That's why this line is a little bit in an E shape, E curve shape, or a parabolic shape, sort of. So when you want to calculate the drain current, there's a formula for that. It's a rather long formula, but basically it is the drain current. We can calculate that. So it's 1 minus the voltage on the gate divided by the gate source voltage on the gate when it's off. And we divide that by this, and then we can calculate the drain current. But the drain source voltage must be bigger than the drain source voltage at pinch off. That's what that P stands for. You don't have to worry too much about it. We won't really ask that in the exam, but just learn this formula here. So this formula doesn't apply in a special case, but we are not doing that really deep into that in this class. People, why are you so silent? Are you totally amazed by this new event happening here about FETS? Do you have any questions? Does anyone have any questions for us? Right, I'm getting on now. So there's an example here. This example will really help us to calculate the current here in the drain source, that current. So the gate source voltage is 0 volt. The ID is IDSS, which means this current is the same on top there as in the bottom, which is in 10 milliamp in this case. So we choose a current of 10 milliamp here. And if we have a resistor here in series, we can actually calculate the volt drop over that resistor, because we know that the drain source current, this main current, is 10 milliampere. So we need to calculate ID, the drain current, for each value of gate source. So this gate source voltage, the voltage on the gate, can be either 0 volt, or the gate voltage can be 0.5 volt, minus 0.5 volt. So there's a case A and a case B, and we must calculate the drain current now for these two. So the first one, there it is, the drain current is 10 milliampere times 1 minus 0.5 volt. This one minus 0.5 volt divided by minus 4 volt. Minus 4 was the pinch off voltage. The VG is off. You see VG is off. The pinch off voltage there is minus 4 volt. So 0.5 over 4. And then we multiply that, and then we get the current is really now 7.65 milliamps that will flow here. However, we go to this one, and the previous one we had minus 0.5 volts on gate source. So we can now put minus 1 volt for gate source here, minus 1 volt, and then we can see how this current now decreases, because that voltage, we made it more negative. Remember the previous one, it was minus half volt, now it's minus 1 volt. So the current decreased. That shows you how the current decreased when we use this formula. However, if we go more negative on the gate, minus 2 volt on the gate, the current will even further decrease. And this formula shows us there is your current, your decreased current. So remember, just remember one thing, this 10 milliampere is the maximum drain value that's allowed for the FET. And they call it IDSS, which is 10 milliampere in that case there. Now, ID is the absolute maximum current for the FET. But the current flowing due to the control of the gate voltage, we call it ID, which is the answer here, this one, ID. And that is in this case 7 milliamp, due to the fact that we've put a negative voltage here now at that point. And therefore the current reduced from 10 milliamp to 7.6 milliamp. And these examples just do the same thing to show you how the current decreases all the time. The moment you make the gate voltage here more negative there. And even if you go minus 6 volt here, this current will be like in the microamps. It will be like 10 microamps later on. The more negative you go there. So JFET biasing techniques, it also has biasing just like bipolar transistors. So we've got a few bias methods. The first is the gate bias. We call it a self bias. And then there's a voltage divider bias, which is similar to the two resistors on the base of a BJT transistor. Remember, we had two resistors on the base. This voltage divider is the same as that. And then there's also a current source bias. There are 4 biases. So let's look at the gate bias. This is basically, I'm just going to make this a little bit smaller. So the gate bias is when we've got a gate here, and it's the one we've done now the whole time, the last half an hour. It's with a negative voltage here on the gate. It's the same one. It's a gate bias. A voltage divider bias when you have a resistor there on top, as well as another resistor down here, which forms a voltage divider. But in this case, there's no voltage divider. It's just one resistor to a minus voltage on the gate. So a negative gate voltage applied through a gate resistor, RG, there's your gate resistor. And since there's 0 current in a gate, the volt drop or RG, the volt drop here is 0 volt. There's no volt drop over it because there's no current flowing in a gate. Never is there a current flowing into the gate. Right, the main purpose of the gate resistor is just to isolate the gate from ground. So when you've got an AC signal input here, we don't want this point connected to ground here because the signal cannot come in. That is the only reason why we put a resistor here. Now in this figure, it shows how an actual AC signal is coupled into the gate. So let's show that. So here's the gate. We've got a gate bias resistor here to ground or to a minus value there. And then there's a capacitor here and a sine wave input AC comes in through the capacitor and the sine wave goes into here and it will appear here on the output, on the drain output. This is the drain on top and this is S, which is the source here on the bottom. So if we shorted that and no resistor to the ground there, then no signal will get through. And that's why we put a resistor in here. Usually this resistor is like 50 ohm or so, sometimes 100 ohm. It's very low resistance that we use here for the gate. Now the input impedance for a FET is very high. So the input impedance, the resistance and a FET on the gate is very, very high. In that case, we can use a very high resistance here. Like here in this case, a 1 mega ohm. Sorry, I said less than 100 ohm. It's not true. It's like a mega ohm here. Sorry for that mistake. It's about a mega ohm here in the input. All right, the input impedance is very high, and it's about a 1 mega ohm in this case. While for BJT, the input impedance is very low. Therefore, that one it's very low here. Okay. We're always comparing FETs with BJTs, and there's always this comparison between them. So now we can calculate the voltage on the drain source, on the output, basically. The voltage on the output is VDD minus the current in the drain times the resistor in the drain, because there's a volt drop over that resistor. That resistor volt drop will form over there. That's why it's the current in the drain times the resistance in the drain. Let me go to the picture. The current in the drain is this current, and the voltage over it is the voltage over this resistor here. So ID times VD gives me this volt drop. So this voltage, VDD, is 20 volt, your power supply voltage, minus that voltage will give you the voltage over here, over the drain source. If I want the drain source voltage here, it's just like a BJT transistor. This voltage, according to Kirchhoff voltage law, this voltage plus this voltage equals to the supply voltage. So if the supply voltage is 20 volt, and this is 5 volt over this resistor, then this voltage here will be 15 volt. Kirchhoff voltage law says that this voltage plus this voltage equal to the supply voltage of 20 volt. Guys, is that clear? Any questions on that? You can ask while I'm talking. And therefore my formula to the voltage on the drain source is the voltage on the power supply minus the voltage of that resistor on top that I showed now. The gate bias is rarely used because the characteristics for the individual FETs vary over long. So we don't use it much. We don't like to use gate bias. We really like a voltage divider bias there. We like that much more. So I'll get to that now. So let's just look at this example. In this case, there is your FET sort of gate bias resistor here. And now IDSS is 2 milliamp and the maximum current is 20 milliamp. So it can vary between 2 milliamp through here. 2 milliamp to 20 milliampere. It says it can vary here. So for the FET parameters shown, calculate the minimum and maximum voltage values for ID and VDS. So the minimum and maximum voltage for ID will be 2 milliamp times 1 kilo ohm, which is 2 volt. Okay, 2 milliamp times 1 kilo ohm. The volt drop here is 2 volt. So remember that. If that voltage is 2 volt and this is 20 volt, what is this voltage here? The voltage on the drain source will be 20 minus 2. So this voltage will be 18 volt here. Does that make sense? However, if I have 20 milliamp current flowing through this one, through this RD, 20 milliampere, the volt drop will be 20 volt over there, over that resistor, 20 volt. And therefore, 20 minus 20 is 0. So this voltage will now be 0 volt. And it's saturated because this thing is fully on. It's saturated just like BJT also gets a saturated voltage, and it's like almost 0 volt here sitting over it. So 20 minus 20 is 0. So here's a calculation also that shows that. And what we can do is begin calculating ID and VDS using the minimum values for the IDS and the voltage on a gate source. So if we take 2 milliampere for IDSS, then we apply to that formula above that we learned 10 minutes ago, and we put minus 1.4 volt on the gate, and in this case minus 2 volt, which we calculated because of that 2 milliamp gave it 2 volt voltage there. And then we can calculate it. Now the new drain current will be 125 microamp. And the same will happen for the maximum current case, which was 20 milliamp. We can do the same calculation, and then we get 19.87 volt over the drain source output. So these two formulas are then used in the case where the gate source voltage on the gate is minus 1.5 volt. Then we use this formula to calculate the final values. People, I think I'm going to stop here. Is that very clear to you right now? Do you have any question on how to calculate this? The current through the drain source. Oh, sorry, the current through the drain now, which is the same as the current through the source. Those currents are the same. Are there anyone who's got a question on this? Okay, I just want to see what else we can just see what other theory is here. There's a further example where we've got the resistor in the drain as well as a resistor in the source. And this one does work the same as a BJT transistor, where we had this current is the same as the current in the bottom. So whatever current there is will also flow here in the bottom, and you calculate this volt drop, and you can calculate that volt drop. And in this case, they call it the self-biasing. This is self-biasing, and there's now a resistor here as well as here. So for self-biasing, and this is the load line, they draw the load line like this, and the Q point is 5 milliamp, and the Q point voltage there is like minus 1 volt on the gate. And in the third case, you can go through this calculation. It's just the same as the previous one. And then the next one is also an example. And the next one is the voltage divider bias. In this case, we've got a voltage divider on the gate there in there. It's just like the voltage divider we have for the BJT transistor. And these two resistors will form a voltage divider. It will divide that voltage of 15 volt into these two values. And this formula calculates now the voltage on the gate. And you use the voltage divider formula, which we have done previously. So now we can calculate the voltage on the gate, yeah. Like for instance, is it like whatever the voltage is. So we can calculate it, and the source voltage is calculated as Vs. It's this voltage here. The source voltage is Vg on the gate minus V gate source. So is this voltage here over this resistor minus the voltage over those two. So therefore, we've got a formula here, and since ID is IS, this current in the drain is the same as the current in the source here, and the drain voltage is therefore VD, which is this drain voltage over here on top, is VDD minus IDRD, which is power supply voltage minus the volt drop over this resistor. And then you calculate VD. Okay. The advantage of the voltage divider bias is it's more stable. So it's just a more stable design than a gate bias or a self bias. So learn what this advantage is. You must know this in a theory. A drawback of the voltage divider is the value of ID for a given gate voltage varies between J FETs. So that makes it difficult to predict the exact value, because every J FET that you buy in a shop is slightly different from another J FET. So that's one of the drawbacks of the voltage divider bias. All right, guys, let's stop here, and I'm going to stop the recording, and I'm going to ask you first if you have any questions on this, and must I go back? Is there anyone that something is unclear and I must go back? If you have a question on this work. Does anyone have a question? People, can you still hear me? You are totally silent. Is there someone that can hear me? I'm going to stop the recording here. I'm going to stop the class here. Next week, we'll carry a little bit further, and then also we'll do op-amps. On Monday, the people that failed, especially those failed below 40, can get another chance to do the makeup test. That's the last makeup test before predicate day. And those that doesn't pass, they cannot write the exam. So please come Monday, 10 o'clock, and write that makeup test. Monday, 10 o'clock, there in building 4. Thank you, people. We can building 4, room 4214 and 4207. Those rooms, we'll see if we can write the test there. Any other questions on that, on the test and on this new work about field effect transistors? Raboya, Mabuela, do you have any questions? Sherry, do you have any questions on this work? I'll take the recording, Sherry, and I will WhatsApp the link to you for this recording later tonight. And then you can send it on WhatsApp to the other people, that YouTube link. Okay, thank you very much. And enjoy your test tomorrow and your work and your test to Monday also. Thank you. People, are there any other questions? Nobody. Nobody's got anything for me. I think you are totally amazed that such a thing like a FET can exist, but it does. And yeah, unfortunately, we have to learn those things as well. Guys, just I'm not sure if you're still here. We don't do FETS on Monday. FETS is the stuff that I've done yesterday with you. So if you don't know, ask Chile, what did we do yesterday? That was the scope. Yesterday was the scope for Monday's test. So we don't do FETS on Monday. Okay.